here. So what I'm going to talk about tonight is anomaly detection. Kind of made a little bit of traffic for myself there with the table. And then afterwards, we've got some books here. You guys can have them. I'll sign them if you want me to. I'll not if you don't want me to. However you want it to work. Can you hear well enough in the back? You guys are good. It's an amazing room there, because that's not how loud I'm speaking. Do you need me to do anything for the sound there? Okay.
You're good.
So what I want to talk about is anomaly detection. And these are general techniques. They have nothing specifically to do with MapR. So we can do it without the hat. But they do have to do with what people need to do with large data systems very often. And that is to find what's going on. This is not the kind of anomaly where you know what's going to happen. You say, that's the kind of failure that I know about. What we're interested in tonight is finding out about anomalies that you don't know about, that you don't expect, that you couldn't define ahead of time, the surprises and things. And I'm going to talk primarily about things that are simple enough. I've done plenty of fancy algorithms in my time, but I find that it's a much, much harder problem to build something that's simple enough that virtually anybody can use, regardless of their necessarily mathematical or whatever qualifications. It's far more important, I think, as well, that the typical teams that are working with a lot of data going by, who tend to be more computer science oriented, more operations oriented, that they can survivably deploy these systems and keep them running. So the techniques I'm talking about tonight have very deep philosophy underneath them, modest amounts of mathematics underneath them, but on the surface are very, very simple and intuitive. And that's what we've been developing. And I've worked on a book, not this book, the book before this, with my co-author, Ellen Friedman. And you can reach either one of us at any time, practically, by these means. And I'll talk more about that in later slides. This is the book. You can get a free copy, courtesy of MapR, or you can buy it at Amazon. If, for instance, we don't have a Kindle edition at MapR, just a PDF. Pick your poison. There's a registration on the MapR side. There isn't on the, well, I guess there is on the Amazon side because they require a credit card. So, I want to talk about that this series of books is about how machine learning is becoming mainstream. It's no longer an obscure topic. It's no longer a thing that people in a room somewhere do. It's beginning to be something that everybody has to do. And so this whole series of books, starting with a book on recommendations, anomaly detection, time series databases, and the latest one, which will be coming out in 2 weeks, are all about practical things that people, real people, can do with data. So let's talk about anomaly detection then, and in particular, a nice, coherent way of looking at anomaly detection that leads to several concrete ideas. Anomaly detection is used ubiquitously. Utility providers have massive numbers of smart meters, and by monitoring those through a mesh network and seeing what's happening, they can find out about outages or other anomalies before anybody can call in. They know exactly what's happened, and they can make projections and dispatch teams on the problems. That saves hours of downtime. Now, modern factories, which this is not, I think they're building old television systems there or something, measure everything. As the production line runs, all kinds of measurements are made. Weights measure temperatures, rates, and anomaly detection is huge in manufacturing. Telecoms, some of our customers are looking at very subtle forms of anomalies in their networks, either for security reasons or for simple things break reasons. And these are major uses of anomaly detection. So we're going to try to find rare events, rare enough that we didn't understand them before. We want to find it before other people find it. That's because otherwise we look stupid. And I'm going to talk about why it's an issue. Now, you might look at a signal. This is a signal. This is normally distributed random data. Now, if I wanted to look for an anomaly here, I might see, whoa, that doesn't look right, does it? Why does it not look right? Why not? I mean, you've got some idea from the first slide that the data looks like fuzz, kind of this big. This thing is standing out of that. In our vast experience on the previous slide, after this one, we've never seen anything like it. Thousands and thousands of samples. Not exactly big data, but almost up to mini data. And it looks odd because we have a conception in our heads of what normal looks like. Now, we also might see it do something like that. We also feel that that's anomalous. And indeed, we might have a signal that every few thousand samples just kind of takes a wild hair and jumps off into the corner. That could be normal. Or it could be that every few thousand samples, it shifts its baseline. Either of those could be normal. And it might even be that one of them is a failure that's fairly common, the other is a surprise. But either way, we have to decide what do we think normal really is. And then we have to decide how to find deviations from what we think normal really is. And in this case, normal includes everything we understand, including well-understood failure or abnormalities. So we can't just use a simple model if this is part of normal. We would have to use some sort of mixture distribution to model the things. We can't just use a simple model if both of these are kinds of normal. We would have to use something slightly more interesting. But either way, finding normal, building a model of that is the key here. We'll talk more about that. So the basic idea is we're going to build a model. We're going to understand the data that we have by building that model. And in my sense, understanding the data means being able to, as much as possible, predict it. Possibly over a very short horizon. But to my mind, prediction, in a probabilistic sense, is the essence of understanding. We'll talk about that much later. And then we're going to decide how far away, how implausible is this recent data, and therefore how anomalous. And we'll use that new anomaly detector to find anomalies. And we may find that some anomalies occur enough that we want to characterize them and make them part of our conception of normal, and then continue to look for surprises. That's fine. This is an iterative thing. All of these are forms of ways that we can begin to understand the data. Now, anytime we do that, we're going to have a problem. If we set the threshold here or here, we're going to miss that data point, which may be an anomaly. And we'll definitely miss this one. If we move the threshold down, we're still going to miss this one. If we move the threshold down enough to catch all three anomalies, X's, then suddenly a lot of the normal things begin to be marked as anomaly. We're going to always have this trade-off, and we're going to have to make that trade-off intelligently. Now, in practice, in my experience, the most intelligent way to do that is to budget how many times do you want to get up in the middle of the night. And I don't care if it's a false alarm or a real alarm. I want to know about how many times I'm willing to do that before I get stupid enough that we start losing other things in response to these. So I'm going to set a budget. Anomalies, not anomalies. I'm going to set a budget for how many alarms I want. And then I'm going to try to optimize the fraction of that budget, which are true alarms. But the basic idea then is I'm just going to set a threshold that is low enough that it hits my budget for alarms, and then make it be as good as possible in terms of false alarms. So I'm going to set an adaptive threshold. And I'm going to set it based on the budget that I have. We don't want to set too many false alarms. We don't want too many false negatives. But instead, we want to match that budget. So what's the easy way to do that? We can use an adaptive threshold, which purely looks at the historical percentiles. That's going to meet our budget. Now, it'll blow the budget when things really go bad. Yeah, that's not such a bad thing. We can set that to whatever threshold we like. Now there's a new algorithm, T-digest, which does exactly that empirically, very efficiently, even at high quantiles. And at, say, the 99.9 or 99 percentile, we're going to get part per million accuracy in the quantile space. So we can do that now very easily. Simple plug-in. We're going to have this online summarizer, quantile estimator, and a threshold. Works for the problem we've seen so far. The internals of how the T-digest works is that it keeps a lot of accuracy at these tails. It keeps essentially a one-dimensional k-means algorithm. It allows the centroids in the middle to become large, many samples, and therefore have rough estimates of the quantiles in the middle. But then the clusters at the edge are constrained to be very small. That allows us to constrain the relative accuracy relative to the distance of the tails and make that a constant. And that gives us exactly the properties we want for these thresholds, which is very, very accurate at the tails. Okay, so looks like we're done, huh? We just make this thing with the extreme tails, find those, we can go get it off of Maven, anywhere we like, we can integrate it very easily. So what's the big deal? It's even available in Elasticsearch, it's available in Mood, it's available all over the place. Done? No, we're not done. We could integrate that into software like ODSC's Skyline, but we still have signals like this. This, by the way, the nature of this talk is I'm going to say, see, we're done. Oops, we're not. See, we're done. Oops, we're not. This is the first oops, we're not. The baseline here shifts. So a constant threshold is going to find A, that anomaly. It's going to completely miss B unless something like 10% of the data is marked as anomaly. This is untenable. So we're going to have to make that a little bit fancier. We're going to make a model that understands that this is a signal that has a varying baseline and then noise on top of that. Not so hard, not so hard. So we're going to have a fancy model here, subtract off the baseline, and do the same thing. By having that model subtract off the baseline, we get a stationary fuzzball sort of signal again. Looks like it's solved. But what we're doing here actually has a really deep intuition underneath it. Intuition is that this idea of subtracting and then assuming the result is kind of like a normal distribution is essentially saying that difference from that model is, squared distance from the model is effectively the log of the probability. This is the little tail of truth that we've caught onto here. And log of the probability is a very, very exciting idea. The reason, and by the way, the reason that the square turns into log of probability is we're saying it's kind of like Gaussian. E to the minus delta squared would be what the normal distribution looks like. The log of that, of course, is minus delta squared, the absolute value of that. Bingo, there we go. But the point about this is that if we match the system so that the log, as estimated by our model, of all of the things we've seen, the average log of that probability, if we make a system where that is as large as possible, meaning it's assigning as large a possible probability, and it's a valid probability, we have found something that is as close as mathematically possible to the truth. Now, truth with a big D is a big word. And this is validly the best estimate of truth that we can make. Anything that minimizes that log of probability, maximizes, minimizes the minus log, is truth. Truth as well as we can. So this is a big deal. And as such, the thing that drives us to that, the magnitude of that is the deviation from our model in the sense of how wrong is our model. Therefore, anomalies are most sensitively detected by this kind of model. Well, let's look at another signal. Looks like an anomaly. Looks just like the anomalies before, a little bit fancier. Perhaps not if you saw the rest of the signal. That's a heartbeat. I like to think of them as normal. I'm going to continue in that opinion regardless of the question period. Now, an anomaly in heart rate or heartbeats often looks like this. somebody has an irregular heartbeat or something like that. This is far more complicated than just the shifting baseline. We're going to have a much more interesting model to model that in the sense of minimum probability. But this is still a continuous time signal, and we can still do that. Here's a simple way we can do that. What we can do is we build this model, and we're going to say that the deviation here. This is what we're going to do. We're going to take the original signal here, and we're going to multiply it by a window. A window signal is merely a signal that's mostly zeros. Only in a finite region and small region is it non-zero. And we've chosen it so it has nice properties as well. This is sine squared in this region. And the nice thing about sine squared is if we move it over a half step and add them together, move it a half step and add it in, move it a half step and add it in, this truncated sine squared, these values will all add up to exactly 1. And so if we multiply our original signal by these and get these little windowed pieces of the signal, then shift this and get another little piece and add those together, we come back to the original signal. It's distributive law. Since these add up to 1 constant, then multiplying it first and then adding adds up to the original signal. That's a nice property. Furthermore, if we look at this little windowed signal, 32 samples there, and we shift this, oh, that looks a lot like the first one. And there it is again. This is a quasi-periodic, kind of sort of periodic signal. And so we see the same shapes again and again. Perhaps not situated exactly in the window at exactly the same point, but we do see the same things over and over again. And so what we can do is we can actually take these windowed values, these 32-dimensional signals, short signal chunks, and cluster them. And since we're interested in it as a continuous valued signal, squared error is a nice natural power error sort of thing, we can use k-means clustering because it is minimizing squared distance of the centroids to these little bits of signals. And if those centroids are close to the signals we've seen, then we can just substitute the thing in the window by that little chunk of centroid, that little average value. And then we can add them back together and reconstruct our signal. Here are the first 64 most common of those signals. And if you look there, and there, and there, and there, you see variations, slight shiftings of that pulse that we talked about before, the QRS complex, as it's called. And so these clearly represent something like the original signal. Now these are scaled. So this bump here and this bump here were very small in the original signals. All we care about here is the ability to recreate the original irrespective of the magnitude of it. We'll let the scaling drop in as well as which one of the signals did we pick. We aren't just going to pick which cluster. We're also going to pick a scale for each one. And here's what it looks like when we reconstruct it. The top is the original. The middle is the reconstruction. By finding the closest centroid, scaling it according to the dot product, and inserting it back in as if that were the original signal. And this is the difference. The only errors that are large are at these areas of high slope, where very slight offsets in time can cause relatively large error. But you can see the error is almost never of 50 plus or minus. It's a lot like, not really quite like, but a lot like that first signal we talked about. And we could put a threshold detector on that. If we did that, then this is what an anomaly looks like. See that right there? Suddenly we get signals up to 150 either way. Something went very wrong. If you look at this original, it doesn't look that different, but the reconstruction is wrong. Very, very wrong. It doesn't go down the way the original signal does. Here's a magnification. That's the beginning of tachycardia. So it's very, very abnormal and very bad for you sort of thing to happen to your heart. And the reconstruction says, I can't understand that as a heartbeat. It doesn't look like the things I've modeled. And so the reconstruction error is very large. It's positive and negative, and positive and negative. Squared error, even average squared error, becomes quite large there. So we've detected a real physiological anomaly here by finding something that doesn't look like a heartbeat. What does look like a heartbeat means? It means we've built a model of what heartbeats look like. It's a complex model. It's not a simple little Gaussian distribution. It's a complex model that incorporates essence of heartbeat, at least simple essence of heartbeat. Doesn't really incorporate heart rate. It's just shape in a small region. I'll talk about how to extend that later. But then it finds places where the shape is wrong. Shape is wrong because it doesn't match the model, which was made as much like real heartbeats as possible. This is kind of cool. I mean, Saturday afternoon's level of effort, and we have an anomaly detector that finds interesting anomalies and goes through hours and hours of heartbeats that do not have anomalies without alarming. So, cool. I mean, this isn't that hard to build, and it's easy to extend to much more elaborate and interesting signals. This is an example, in fact, of a neural net. This is a neural net autoencoder, a very simple one. And we can make more complicated and interesting ones to do more interesting things. Here's another anomaly. It doesn't look like a heartbeat on the top. The poor model finds it impossible to reconstruct because it doesn't look like a heartbeat. Here's the anomaly signal. This is not a physiological anomaly now. This is probably an electrical anomaly. Somebody rolled over in bed or something like that. But it's still an anomaly. It doesn't look like a heartbeat. We still get a valid alarm. It's cool. So the idea was that we build a model. It doesn't have to be a simple model. It could be a moderately complex model, but it has to really reflect the signal we're after. And then we can look at the online summarizer and find the right place to put threshold, and bam, we find double heartbeats and missing leads. Somebody called ground lead. Okay. This is a model delta anomaly detector. The delta is roughly the log of the probability, because probability we assumed is this idealized signal plus small noise. Small noise being Gaussian. Okay. But this isn't going to work for signals like when did somebody come into a website. Those occur spaced in time at variable instances. There's many people, we hope, come into your website. They're going to be all independent. We hope that they don't all collude somehow to come in at the same moment. They're generally independent. They can't communicate on millisecond timescales. And so the thing is like raindrops. They come in with these variable rates. We can't really build a continuous signal because their arrival is an impulse. It's not a value that goes up and down. They are there or they are not. There's little impulses that occur separated in time, sporadic events. So to model these, we're going to have to do something different. We might want to look at it because we want to see if business has stopped on a website. Has it broken? And this is where I started, actually. We had a website, a music match, and at 2 in the morning, the CEO would wake up, suddenly afraid that maybe things weren't right, and he'd go to the website and check it out, and then he'd call me at 2:15 in the morning and say, Ted, we haven't had any sales in 15 minutes. Don't you think that's a problem? I go, well, yeah, it's a problem. You called me at 2:15 in the morning. It's clearly a problem. Now, what exactly was the problem is another question, but it was clearly a problem. So there were 2 problems, 3. One is, and this is just a general thing, he was often right. There often were problems with the system. Now that leads to a second thing. You must never let CEOs be right about these things. You need them to be going off and selling the company to Yahoo for great grand sums of money instead of waking up with really minute questions about, is the e-commerce system not right? Write down. If he wakes up at 2 in the morning, he's not going to work well the next day. And generally, it's bad for them. New CEOs really need to be trained carefully so that they sleep through the night. You have to bring them along gently. And if you do good education, they sleep and they do the things they're supposed to do. They develop as CEOs and really become excellent things. And so, clearly to me, the real problem was Dennis was finding these things, shouldn't say that. The CEO was finding these things before I found them. That was the real problem. Whether or not the system is broken is a secondary problem. We can fix broken systems if we know they're broken. The real serious problem is the CEO is finding out before the guy in charge of the team running the system. That's a huge problem. So we built an anomaly detector to find these sporadic events, sales, which are roughly decoupled in time, and find out when it had been too long since the last sale. Very quickly after that, what would happen is my phone would ring, the computer calls, I'd get on it, and 10 minutes later, Dennis would call, or half an hour later, I'd say, Dennis, where have you been? Dude, we're on this. We've been on this for a while. We've identified this, and he began to sleep. And he began to do a much better job because we had elevated his levels of concerns to large-scale things instead of small-scale things. So this is a very successful thing. It bought my car and a bunch of other things for me. Anomaly detection can be a very good thing. And furthermore, we found out what the thing was. It's very hard for technical teams to believe it when a CEO says something technical. It's just the way of the universe. And therefore, they wouldn't fix it, really. You know, he just complains. When it's their own system that says it's broken, they wake up and they're on it. They own it. We owned it. We fixed it. And eventually, we sold a crap load of these audio jukeboxes. We were the most used thing on the internet for audio, more than Microsoft, more than anybody. So we won by doing this kind of model. So, basic idea now is time between events is something we have to convert because we can't convert the magnitude to a thing that's useful. Now, time between is much better than counts. Many people use counts, say the counts over the last 10 minutes, the counts over the last hour. The counts over the last hour are clearly unacceptable for this problem because the CEO will call you partway through the hour and you will be unable to say anything. You have to wait a long time for the counts to be large enough counts to be significant. You can get the noise levels down. Time between events, however, time between the consecutive events, time between the nth events gives you a much more optimal detector of failures of different kinds. Time between individual events is the most sensitive detector of stoppages. Time between the nth events is the fastest detector for high-low sort of rates. And you can put noise levels on these. So we don't use counts, we use time interval. And furthermore, if the events coming in are Poisson distributed, meaning the events come in at a constant rate and are uncorrelated, time between events is the log of the probability. It is the best anomaly detector we can have. So that's an exciting thing. That's a big deal in TM or whatever on that. So the key question is whether the frequency has changed. Because I said constant frequency, and we know that's not true. More people buy during the day than at night. So it might be okay for 10 minutes to go by during nighttime, but it's not okay for 30 seconds to go by during the day. So the rate has changed. We have to model that somehow, and we want to alert as quickly as possible. Here are times between Poisson events. There's a lot of fuzz on that. They're always positive, of course, but we can put the thresholds on them just like before. Here are events and times between things where the rate changes. I've arbitrarily made it up. This is all synthetic data. This is the rate. Scale's on the right. It goes over an 11 to 1 range. This is sine to the fourth plus 0.1. It's nothing magical. And each day, in the middle of the day, it goes high, and at the edge of the day, it goes low. And here are the times between the events, the circles. During the night, the times when events are big. During the day, they're short. And we have lots of data points here, very few data points here. So we don't want a constant interval because it would be too long during the day and too short at night. We want the interval between the events. But they vary. It's like the signal that went up and down. We need a more elaborate model. So we can look at this. Over a short time interval, this rate in the Poisson model is going to be constant, and so the minus log, that the probability is greater than a certain amount of time, is lambda t. If we could just make lambda t be some function we could estimate, we would have something that would scale it. And here's a picture. The clear bars, which you almost cannot see, you can see one peeking out there. You can see that they're slightly behind the pink bars in other cases. The clear bars are high rate time intervals scaled by rate, and the pink bars are low rate events scaled by rate. And you can see they have very, very much the same distribution. And so our thresholds work after we scale by rate during high frequency and low frequency times. And so all we need is to extend this original thing to something that has a rate predictor here. And then we use the difference on times. And now we get this delta here. And that lambda is the scaling factor that makes it log probability. All we have to do is build a rate predictor. All we have to do. Well, that's better than what it was, so it's not entirely funny, but it is still worthy of little fingers. Here is why it's hard. This is the main page to Wikipedia for November, the beginning of December 2008. And I've plotted two curves here. One is the traffic, and one is the traffic of a week ago, relative to each point. It works not so bad as a predictor until you have little count anomalies. Well, those were anomalies. Somebody wrote down the wrong numbers on that. But then on Thanksgiving Day and the day after, it becomes just what we in technical terms call broken. Now, you can see interesting things in this traffic stuff right there. You can see the traffic going up, and then at noon it drops down. That's when everybody sits down and stops looking at Wikipedia. They start eating. This is kind of one of these heartwarming observations. There is something more important than looking at the internet. Still, well, at least in 2008 there was. But 1 week lagged data is not a good predictor. This is commonly used by websites, and they commonly get so many false alarms that they just ignore them. Commonly, as in when looking at access times and things like that, Target, and Home Depot, and basically every other big retailer ignored the alarms they were getting from their anomaly detectors because they had bad rate information, and they go off all the time. But it's really easy to make this better. Now here's a harder problem. Here's the 1 week delay thing. Now this is the page for Christmas going into December. And oddly enough, somebody, I don't know who, is looking at this page more and more leading up to the 25th of December, and then the traffic crashes. And on this, the week ago model is just completely disastrous. It goes low, it goes high, always at the wrong times. But we can do much, much better than this. Watch this. With our little rate predictor, what we can do is we first talk about predicting the log of the rate. The reason we do that is people talk about peak to valley ratio. They talk about traffic growing by 30%. That's a factor. They talk about all of the rates are positive. You never have negative events per hour. So this really sounds like log sort of things. And log sort of things are best handled by modeling the log. And of course, because I said so, and I'm such an experienced guy. But you get the feel for some things you treat in log space, some things you treat in their normal habitat. The only virtue of doing this is it allows you to have a linear model. And so We can let the model see many old values from 1 hour ago back to a couple weeks ago, and we can let the model, a very simple linear model with a nice system for eliminating most coefficients from the model, look at those lags and build something nicer. This is what we do. We build a data set like this that has the current value and all the lag values of interest and a time, and we're going to build a model that predicts this from these. And here's what that looks like. I trained it only on the last half of November and told it to predict an hour ahead throughout December. And you can see that except on Christmas Eve and Day, it was, well, even then it was within, I think, within 20%. The rest of the time, much, much tighter. And then even on January, on the days after, still pretty tight, again, within 20%. This is a first hack, again, Saturday afternoon level of effort. You can build very nice models of these. And now we get, even over absurd change of behavior, you get pretty decent predictions of behavior. You would not normally predict, based on Thanksgiving, what's going to happen on Christmas. Just not what you do. You would predict based on last year and all the way through now. So we can build this. We can build these anomaly detectors for rates, or not for rates, for intervals based on rate models. We can build signal detection models by very simple means, and we can find anomaly detectors that really do this well. Now, it's best done with a probability model. There's probably enough people in this room to be interested, but there's actually a very simple mathematical proof that this is the best way to approximate truth, to find the model that is closest to the true probability distributions, and therefore is the best way to make probabilistic estimators that have minimum false positive, false negative trade-offs. So I can go through that afterwards if anybody wants, but this minus log p can take different forms. We can build these models. I give more examples in the book. And fairly simple distributions do work, but completely simplistic distributions don't work. And we can do the quantile estimation to get that right. Different systems require different models, contiguous systems, or can use sparse coding or something like that, deep learning. Events in time can use variable rates. If we have events with labels, like you log in, these images get downloaded, you type in certain keystrokes, and we get those in time, we can actually build very elaborate recurrent neural net sort of models, or even simple Markov models, to detect human versus non-human behavior. And they can separate very interestingly. Applicable across a wide variety of places. Here's a catalog, a visual catalog of the techniques. The last one here is the one I didn't talk about, which is the fraud modeling using sequences of symbols. And we've got a book on it. You can download, as I mentioned at the beginning. And there it is. We also have other books available. The time series database that we have here tonight. And coming up in 2 weeks is war stories from customers that MapR has. We've got a lot of them now, and there are beginning to be real regularities in the problems that they succeed on, the problems they have trouble with, not necessarily even technical problems, just problems that are hard to sell in different kinds of industries. And so this book kind of distills down into 90 pages our experiences in those areas with some good hints, I hope. Thanks for coming today. And we're going to have some questions, and then about 30 books up here for anybody who really wants a copy. Probably we ought to stratify by people who most want the copies. So just for fun, and then maybe let somebody else have it. Are there any questions? Good, I was hoping there would be.
So if you have multiple streams of data, and the anomaly you're trying to detect is actually the anomaly in the correlation between those streams, would it be the same approach, or is it more
So if you have multiple streams of data, let's take a municipal water system. Let's take a house, my house. I have, oddly enough, put temperature sensors right at the hot water heater and 2 feet away. And on every faucet, hot water faucet in the house. And so we should have now 12 something, if I go crazy with the temperature sensors. And we should see patterns in time and across these signals. The water heater, right at the water heater, should be kind of like the water heater, but it will spike as water starts coming out of that, because the pipe will get hot. Just a moment later, the pipe will get hot downstream from that, and then 30 seconds later at the faucet. Now, if I ever see that pattern of gets hot near the water heater and then downstream of the water heater, and none of the faucets get hot, I have a leak. Now, I can easily build a representation which takes, like every 10 seconds, takes the last 5 or 10 samples of these 5 to 12 signals and embeds them in some sort of space, and it's going to be smooth and continuous. And we will be able to see non-physical, non-plausible anomalies. If the water starts running at the water heater, the hot water, it damn well better start running pretty soon at the faucets, heat up at the faucets. Maybe it stops heating at the thing, so just a very short thing, I never got any hot water, that's okay. But if it really starts running for a couple of minutes, then something's wrong. And I could have saved $12,000 in my house by having something like this that went on. I was very, very lucky. We were about to leave town. I walked across the carpet, and the plumbing in the slab had stopped working. It started leaking. And that was, of course, always the hot water that does that. So we could really build that same sort of thing, exactly like you said. Multidimensional, as opposed to, so what I took here was a one-dimensional signal, the heartbeat, but I embedded it into 32-dimensional space, state space embedding. But you can do that with multidimensional systems, both by successive time samples and by more measurements. You want a prize for asking a good question? We see your technique there too. Somebody's playing cricket.
Yep.
Oh, now everybody wants to ask a question. A good one. Yeah.
Actually, very similar, but incorporating a multi-dimensional, let's say, I don't know, let's say you're monitoring network traffic, and you're seeing traffic change, and you're seeing changes in application, but you're also seeing changes in packet size, changing in protocol, TCP, UDP, different flags being set, different ports, different destination ports, different source ports, etc. You can incorporate the whole system. I mean, I can analyze each one of those factors separately and say, oh, that's changed, and then try to find. But I'd like to do them all together and say, like, holistically, this traffic has changed significantly, not just in terms of packet rates. But
So let's walk through. What do you know?
Okay.
IP addresses, inside and outside.
Yes.
Okay, those are symbols, kind of a billion of them inside. Packet sizes, you mentioned that. It's like a continuous number, it's integers, but it's got magnitude that's small with respect to the integrality of it. You've got time. When did it happen? Time between connected packets, especially if you're using TCP. So what kind of rates are happening. That would tell you, for instance, a file copy to your own machines might run very differently than a file copy to a pirate who's trying to keep his traffic low. And where these things go and what rates they go, what times they go, should be highly idiosyncratic. Now your timings are going to be complicated because people do complicated things like every hour except, 24 times a day except when, daylight savings kicks in, things like that. So you're going to have kind of a complicated model in pieces of this. You're going to want to see if you can factor it reasonably to keep the dimensionality down plausibly. One way to keep the dimensionality down is to define classes of IP addresses, classes of sizes, so that instead of all of the sizes expressed as continuous variables, you have quintiles, say, or inside, outside IP addresses, these different security designations. Now, you can still keep the full dimensionality available to the models with good modeling techniques. you can leave those in and still learn pretty well. And yeah, you can do this. I can't say much more, but you can do this. Yeah. Yeah.
Two related questions. One is, in your approach, you've never used something like Fourier reconstruction of the signal. And I'm curious what...
Wait, just a moment. Before you go further, you said my approach. I claim no ownership here. I claim curatorial powers, but no more. Because the T-digest is a slight bit of invention, but the rest is purely a distillation of these is what the people in industry do well. They often don't talk about it much, but these are the things that really, really do work. So, not mine, but yeah. So you ask about Fourier transforms. That's
I'm
exactly
just
what.
saying, as far as using that to reconstruct. Another question is, it wasn't clear to me